So, have you ever actually stopped to wonder how your everyday map apps successfully navigate you around town? Mathematically speaking, you literally cannot flatten a sphere without severe distortion. It's a massive spatial puzzle that has challenged map makers for centuries. You simply can't take the surface of a globe and lay it perfectly flat without tearing it or stretching it completely out of shape. And yet, the phone in your pocket does it flawlessly, every single day. Welcome to the Explainer. Today, we're demystifying projected coordinate systems. We're going to treat complex map projections not just as some abstract cartography concept, but as the high-tech engineering challenge that makes modern navigation possible. Here's our roadmap for today. We're going to cover flattening a spherical world, the UTM coordinate system, that mysterious 0.9996 scaling factor, the Gauss-Kruger alternative, and finally, transforming coordinate systems. Let's get right into it.
Part 1. Flattening a spherical world.
To get pinpoint accuracy for regional and state surveys, cartographers rely on projected coordinate systems, or PCS for short. These are grid systems that use metric coordinates. But you know what the big secret is here? They actually ditch the whole globe. Yeah, entirely. Instead, they use a much more mathematically manageable reference surface called an ellipsoid. And the trick is, they only attempt to map a very limited area, what we call a meridian zone, at any one time. That's how they keep the distortion totally tolerable. Think of it kind of like peeling an orange. If you try to mash the entire peel flat on a table all at once, what happens? It tears, right? It stretches out of shape. It just doesn't work. Same thing with the Earth. This is exactly why we use that ellipsoid reference surface. Instead of squashing the entire globe, we just cut out a very narrow vertical strip. By doing that, the flattening process has significantly less distortion. And this brilliantly illustrates the fix. Imagine encasing a wireframe Earth inside a glowing cylinder, but turned completely sideways, a transverse cylinder. By doing this, cartographers can slice out a super narrow, like 3 to 6 degree zone around a central meridian line. Then they just take that precise, limited strip and unwrap it perfectly flat onto a plane. Moving on to Part 2, the UTM coordinate system. Back during World War II, military engineers basically took this orange peeling concept and turned it into a universal standard, the Universal Transverse Mercator, or UTM system. UTM chops the planet up into 60 individual 6-degree strips, or zones. It projects points into a flat grid using a transverse secant cylinder. Now, secant just means the cylinder geometrically cuts slightly through the Earth's surface rather than just floating on top of it. But when you build a grid like this, you run into a very practical math problem. If your center line is 0, then everything to the left of it is going to be a negative coordinate. Nobody wants to deal with negative coordinates, so to avoid that on the left side of a zone, engineers applied a really clever trick called a false easting. Basically, the central meridian of every single zone doesn't start at 0. It starts at exactly 500,000 meters. It acts kind of like a calibrated targeting HUD, ensuring every single coordinate within that zone stays a positive number. The really crucial takeaway here is that a single physical spot on Earth has specific X and Y coordinates that depend entirely on which 6-degree zone grid is currently active. Take a look at this point P in Germany. If we're using the grid for zone 32, its easting coordinate is precisely 32,579,397 meters. The 32 tells you the zone, and the rest is the distance calculated from that false easting offset we just talked about. But watch what happens if we map that exact same spot using the neighboring zone 33 system. The easting value completely jumps to over 33 million. Why? Because it's now being measured against a completely different central meridian. Okay, section 3. The 0.9996 scaling factor. Now, because unwrapping that 6-degree slice naturally causes the outer edges of the map to stretch out, engineers had to find a way to balance things out. Enter the magic scaling factor, 0.9996.
Here's how they fixed the stretching. Instead of keeping the central meridian perfectly true to scale, this formula artificially shrinks the center line using that tiny 0.9996 factor. By slightly compressing the middle, it actually pushes the true zero distortion intersection lines out to about 180 kilometers away from the center. It is an absolutely brilliant compromise that prevents the outer edges from distorting out of control.
Which brings us to section 4, the Gauss-Kruger alternative. UTM is the global standard today, for sure, but it actually replaced a much older framework called Gauss-Kruger, which was developed way back in the 1820s. Looking at them side by side, the structural differences are pretty clear. Gauss-Kruger uses a tangent cylinder, meaning it just barely kisses the outside edge of the globe rather than cutting through it like a secant cylinder does. It also chops the world into much narrower 3-degree zones. And because that 3-degree slice is so skinny, it doesn't suffer nearly as much from edge stretching, so it just keeps a straightforward scaling factor of exactly 1.0. But this visualization shows exactly why UTM won the international standard. Take a look at the blue curve for UTM. That 0.9996 dip in the middle keeps the distortion much, much lower over a far wider area. Basically, you get more map with fewer errors. In contrast, look at the steep black curve of the Gauss-Kruger system. The distortion just skyrockets the further you get from the center line. And that is exactly why it was restricted to those really tight 3-degree windows.
Finally, Section 5, Transforming Coordinate Systems.
So if UTM is clearly the superior system, what do we do with all the old legacy data? Gauss-Kruger is still heavily embedded in a lot of older official maps and local cadastral surveys. Cartographers can't just overlay old data directly onto a new grid and call it a day. They have to use direct and indirect coordinate transformations. Specifically, they use mathematical models like similarity and affine transformations. These equations carefully translate and align that legacy data safely into the modern 6-degree UTM grids. It is a painstaking process, but it's vital to ensure absolute precision. It's pretty wild to think about, right? Underneath the super clean interface of your favorite navigation app is this massive, invisible mathematical engine. Without those transverse cylinders, those narrow little orange peel meridian zones, and those tiny 0.9996 calculations, every single map in your pocket would literally stretch reality and lead you wildly astray. So next time you drop a pin on your phone, ask yourself, are you starting to see the invisible grids guiding your way? Thanks so much for joining me on this explainer.